For this lesson, we'll be focusing on the most common problem in communication, noise. Noise is defined as any undesirable signal in a transmission. It can be classified as quantizing, thermal, impulse, crosstalk, tone interference, and so on. Since noise is classified as any undesirable signal, there are several different types of categories and subsets for noise. The two categories are internal and external, and under those categories there are several different subtypes. The three most popular ones under internal is Johnson, shot, and defect. External only picked a handful: human-made, atmosphere, and space noise. So let's dig a little deeper in these categories. We'll start with external noise. Now for external noise, we had human-made noise, atmospheric noise, and space noise. Human-made noise is probably the most common one. It's typically created from a spark-producing mechanism such as motor or lighting. And usually this has to do with any external energy that's within close proximity of sensitive equipment. So if you have a motor running next to a transmitter, this would cause human-made noise. Next we have atmospheric noise. This is caused by a naturally occurring disruption in the Earth's atmosphere. You can probably associate this with thunderstorms. The last, we have space noise, and this is produced anything outside the Earth's atmosphere. A common one is solar noise. Now in your PE references, the most common of the two categories should be internal noise. Now for this one, I only picked three subcategories of internal noise. There are several different ones, but these are the three common ones. There's Johnson noise, shot noise, and defect noise. Johnson noise, also known as thermal noise, is caused by thermal interaction between free electrons and vibrating ions in a conductor. Shot noise, also known as transistor noise, is found in electrical devices such as transistors and vacuum tubes, typically introduced by the carrier in the P and N junction of the semiconductors. And lastly, there's defect noise. And defect noise is also known as excess, flicker, contact, pink noise, and so on. There's several different ways to characterize defect noise. And it's a garden variety of type of noise relating to any imperfections or impurities in your conductive channel. Now, as you get deeper in the rabbit hole of how to understand noise, you're going to find a majority of material is going to tell you a majority of noises cannot be calculated very easily. Only a handful of them can. The most common one is your Johnson noise, or in this case, your thermal noise. Now, since your thermal noise is in relationship to temperature, resistance, and frequency, it's easily defined if you have those three variables. So you're going to use temperature, frequency, and your Boltzmann constant. Now, something to be aware of when calculating your Johnson noise is that your temperature is in units of Kelvin. So anytime a problem would give you units of Celsius or Fahrenheit, you need to convert that. And we're going to go over that in example problems. So here's where the rubber meets the road. We already talked about what noise is, the different types of noise, and the most common type of noise and how to calculate it. Now we can express the magnitude of noise for a given device. Those two expressions are known as noise figure and noise ratio. Noise figure is describing how noisy a device is in units of decibels. Noise ratio, same thing, you're describing how noisy a device is, but it doesn't have any units, it's a ratio. Now, since Johnson noise is an easy calculation to determine noise power, it can be used to help determine noise ratio. So now that we determined how noisy a device is by finding the noise ratio or noise figure, now you can determine how that noisy device affects other devices around it. That's where Freese's formula comes into play. Freese's formula is a method of determining the total noise produced by amplifier stages in a cascade effect. So we have an illustration below of one amplifier going to the next, and you can determine the noise ratio of the total system by using his formula. And we're going to go over this a little bit more in the practice problems, that way you get a feel for it. So we're going to start off with an easy example. After researching an issue with a receiver, you determined the signal noise ratio was too low, creating traces of static in the background. To minimize the noise, you have the option of ordering metal film low noise resistors as a replacement for the source resistance. To maximize the power transfer by matching the impedance, the ideal resistance would be between 10K and 12K. Determine the maximum resistance possible based on the following specs. Alright, so this is a lot to take in. In a sense, all we're looking for is resistance between 10K and 12K, but we want the highest resistance possible just to match a power transfer. So let's go over what we know. So the first thing we know is the desired noise voltage. So this is going to be V of N, and this is going to be less than 1 microvolts. Okay, pretty simple. The operating frequency is between 5K and 10K, so we know the actual bandwidth there. And then exposed temperature. They gave us the exposed temperature, it looks like between freezing and a very hot environment. Now, just to give you a heads up, the hotter the temperature, the more noise you're going to have. So if this goes up, temperature goes up, that means your voltage noise is going to go up. And we want to keep it low as possible. So we're going to use our calculation based on the highest possible temperature it's going to be exposed to. Because if you have the resistance based on the highest temperature, then you're going to always maintain less than 1 microvolt. So for temperature, we're going to go ahead and say is 98 degrees Fahrenheit. Now operating frequencies is between 5K and 10K. So we have a difference of 5K. So 10K minus 5K is 5K. So our bandwidth, or our frequency difference, which is this guy right here, equals 5 kilohertz. Now what we want to find is, we're looking for the resistance. We want to know that guy. Well, looking to the right here, I can probably use that equation right there, or actually first Johnson noise equation, to determine what our resistance needs to be. Let me go ahead and bring it down here. We have your voltage equals your square root, and this is going to be 4 times Boltzmann constant, which I'm just going to put a K for now, temperature, resistance, and then your frequency difference. So if I was going to fill this in, it's going to be 1 microvolt equals the square root of 4 times, now this is one that's always given. It's going to be 1.38 times 10 to the negative 23. So I'll go ahead and put it in here, 1.38 times 10 to the negative 23. And this is going to be in all your handbooks and all your reference material, so you don't have to worry about it. Okay, temperature, we talked about is 98 degrees. Now here's the kicker. You got to know that it's in Kelvin. Right now, we just have it in Fahrenheit. So I need to convert this 98 degrees to Kelvin. Well, there's a couple ways we can do that. One way is you can look up in your handbooks and you can find a way to convert Fahrenheit to Celsius and then Celsius to Kelvin, which is pretty simple. That's pretty much, if you want to do Celsius, it's Celsius equals your Fahrenheit minus 32 degrees times 5/9. And if you map this out, it's going to look something like this. It's going to be 98 degrees minus 32 degrees, and then times 5/9. And if we just plug and chug that in our calculator, it's going to give us 36.66 degrees repeating, and that's Celsius. Now, yeah, like I said, I can also put this in my calculator and use a little conversion function. Well, now we have Celsius. The good news about Kelvin is it's very easy to go from Celsius to Kelvin. All you have to do is add Celsius plus 273.15 degrees. And in my case, I'm just going to add 273. I'm not going to do the 1.5. We're not going to be that specific. So for this one, it's going to be 36.66, well, repeating, plus 273. And that's a very easy way of doing it. So anytime you have Celsius, you can always go to Kelvin very easily. And just putting that in a calculator is going to give us 309.66 repeating, and that's Kelvin. So right here, I want to go ahead and put it right there, is 309.66 Kelvin. So now I have my temperature. So that's a little curveball you have to be aware of. Be able to change your units from Fahrenheit, Celsius to Kelvin. So I'll put this down here. So it's 309.66 Kelvin. Then we have times our resistance, which is R, times our frequency difference, which is 5 kilohertz. Tell you what, let me go ahead and clean this up real quick. So we already know how to convert that. So right now I can plug all this in the calculator with the exception of our resistance. R4 times our Boltzmann constant times our temperature times our frequency. And that will actually give us everything but resistance for that one. Let me go ahead and do that just to make this smaller and shorten it up. So I'm going to do 1 microvolt equals, and I'll do our square root again. But I want to plug these right in the calculator with the exception of resistance. It's going to give us resistance times 8.54, and we'll say 7, we'll just round, times 10 to the negative 17. And I'll close that bracket. So we have a little bit more to work with. Well, now what we need to do is we need to get rid of the square root so we can move this guy over here. So what I'm going to do is I'm going to take this guy, I'm going to move him up. Give me 1 second. Now, what we need to do is we need to square both sides. Just get rid of the square root. So what I'll do is I'll square this guy and then square this guy. Anytime you do a square times a square root, these two will cancel out, and now we can square this guy over here. So we got 1 microvolt squared, plug and chugged in the calculator will give us 1 picovolt. That's going to equal resistance times 8.547 times 10 to the negative 17. And I'll close bracket. So all we have to do now is actually take our 1 picovolt and we can divide it by our 8.547 times 10 to the negative 17. And that'll give us our total resistance. So I'm going to go ahead and divide both sides. 8.547 times 10 to the negative 17. Same thing. I hate doing that, but gotta make it easy on me. And that's going to give us a resistance of 11.7 kiloohms. All right, so right there, that's our maximum resistance possible for these particular specs. Not too shabby. So now we've got our feet wet a little bit using the typical Johnson equation here, as well as how to convert our Fahrenheit to Kelvin. Let's go on to the next example. We have another good one right here. You're designing an amplifier which requires an input signal power of 2 times 10 to the negative 4 watts at a room temperature of 25 degrees Celsius with a bandwidth of 4.8 megahertz. The desired signal-noise ratio output shall be greater than 75 decibels. Determine the noise ratio and the noise figure for this amplifier. All right, so we're going to do our usual. We're going to start with what we know. First thing we're going to go over is our input signal. So this one's going to be our power for our signal. This is going to be our input. Is going to be 2 times 10 to the negative 4 watts. We know our room temperature, so we know T is 25 degrees Celsius. Now, like we talked about, anytime you want to go from Celsius to Kelvin, always add 273. And that will give us 298 degrees Kelvin. So now we have our temperature. We have our bandwidth, which is 4.8 megahertz. And we have our signal noise ratio for our output. So I'll say signal noise for our output equals 75 decibels. So these are the things we know. With the information we have here, we can actually find our input noise power. Because if you look at this guy right here, we have our temperature, and we have our frequency difference, and we have our constant down there. So I think we can actually find our noise power for our input. It's going to be our noise power for our input equals our constant times our temperature times our bandwidth or frequency difference. So plugging in here, we have 1.38 times 10 to negative 23. That's going to be times, and like we talked about, 298 degrees Kelvin times frequency difference or our bandwidth, 4.8 megahertz. 4.8 megahertz. That's an easy plug and chug. I'll put that in my calculator. It's going to be approximately 1.97 times 10 to the negative 14. Just for simplicity's sake, we can just say that's 2 times 10 to the negative 14 watts. So now we have our input power noise. Now you're probably thinking, all right, what does that help? Well, we have our signal to noise. So now we can find our signal noise ratio for our input, since we already have our signal noise ratio for our output. Because if you look right over here, I want to find noise figure. Noise figure is if I have a signal noise for my input, I might find my signal noise for my output. Well, my signal noise for my output is in decibels. So I need to actually bring that over to a ratio. I already have my ratio for my input. Now I need to find my ratio for my output. So that's actually very simple. Anytime you want to go from decibels to a ratio, you can follow that method right there. Which for a ratio, if I want to do signal to noise, just as a ratio, I can always go 10 and then times, and this is going to be our decibel, so it's going to be dB over 10. So if I want to plug and chug that in there, it's going to be 10, and then we're going to have 75 decibels divided by 10. It's going to be 31.62 times 10 to the 6. So now I have our ratio for my output, and this is my signal to noise ratio for my output. So that's pretty simple. And all I did here was just take my anti-log of my signal noise ratio output in decibels. So one of the key things you gotta know here is how to take your decibels and go use your log or anti-log depending on what direction you want to go. So let's map this out to look like this guy right here. So I want signal to noise input over signal to noise for my output. Well, for my input, it's right there, signal to noise. So I have 2 times 10 to negative 4 watts over 2 times 10 to negative 14 watts. And this is going to be divided by this guy right here, which is 31.62 times 10 to the 6. And right now, we already have this in a ratio, so there's no point in putting units. So this one, we're going to do a little plug and chug here. So I'm going to try to bring this down, see if I can make it fit. 1 times 10 to the 10, that helps, divided by 31.62 times 10 to the 6. And that's an easy plug and chug. It's going to give us a noise ratio of 316.26. Now again, that's unitless, so that right there is going to be our noise ratio for this amplifier. So now I have my noise ratio, which is 316.26. Let me clean all this up real quick so I can make a little room, and then we can find our noise figure. Well, once you have a noise ratio, you can pretty much find your noise figure very easily, because we have this equation right there. And our noise figure equals 10 log, and that's going to be our times noise ratio. So we have noise figure equals 10 log, and that's 316.26. That's an easy plug and chug. And that's going to give us a noise figure of 25. And that's going to be in decibels. Remember, noise figures in decibels. So right now, we just found our noise figure and our noise ratio. Now, there's an easy way to check this. Earlier, we talked about our noise power being 2 times 10 to the negative 14. That's watts. Now, if we did a signal noise ratio for this guy, it was signal noise ratio for our input is approximately 1 times 10 to the 10. That's when you actually took our signal divided by our noise, and they gave us our signal noise ratio for our input. Now this is unitless. We want it in decibels. So if I did this using our little conversion like we just did now, it's going to be decibels equals 10 times log, and this is going to be of our signal noise ratio. So in this case, for this one, it's going to be times 10 to the 10. A little plug and chug there. And I'll give you 100 decibels. So right now, that's your input signal noise ratio. That's your output signal noise ratio. So if your input signal noise ratio equals 100, your output signal noise ratio is 75. So if your input signal noise ratio is 100 decibels, and you minus your output signal noise ratio, which is 75 decibels, you're going to come up with 25 decibels and for your noise figure. So that right there just verified your noise figure. Another way of figuring it out. All right, let's do one more problem. All right, for our last problem, of course, we had to do cascading amplifiers. We're going to determine the total noise ratio and equivalent noise temperature for each amplifier system. So I want to find the total noise ratio, which is this guy right here, and then I want to find the equivalent noise temperature, that guy right there, for every single amplifier. Well, the first thing let's do, let's find our noise ratios for each amplifier. Well, the way that we can do that is very simple. For this one, I have our power signal and power noise going into the first amplifier. Then we have the output of the first one as well as the input for the next one, and so on. So I can use this guy right here to start finding our noise figures. And that's probably what we're going to do. So the first thing I'm going to do is I'm going to go ahead and write this down here. It's 5 milliwatts over 10 microwatts, because again, this is my signal, this is my noise, and we're going to divide it by our signal output and noise output. So our signal output is going to be 10 milliwatts over 25.2 microwatts. And if I just plug and chug that in a calculator, I'll make it easy, that way you can see what I'm doing, of 1.26. Now for the sake of argument, since we have a minute, let's go ahead and find the noise figure. So our noise figure for the first one is going to be 10 log of our noise ratio. And that's that guy right there. So plug and chug that in our calculator is going to give us an answer of 1 decibel. So I'm going to go ahead and write this up here. Our noise ratio for the first one is 1.26. Our noise figure for amplifier 1 is 1 decibel. Let's do our second amplifier. Let me clean this up. And we're going to do the same thing. We're going to use the same equation right over here, but for the second amplifier. Now the input for the second amplifier is going to be the output for the first amplifier. So this one's going to be 10 milliwatts over 25.2 microwatts. And that's going to be divided by 50 milliwatts over 0.252 milliwatts. So it looks like our power is going up with our signal as well as our noise throughout these amplifiers. And this is going to be our noise ratio for the second amplifier. And if we plug and chug that one in our calculator, it's going to give us approximately 2. So that's an easy one. Now I'm going to do the same thing. I'm going to go ahead and find the noise figure for this one as well. And it's the same thing. It's going to be 10 log noise ratio, which is 2. And plug and chug that in one of our calculators is going to give us an answer of 3.01 decibels. Go ahead and move this up here. So our noise ratio for our second amplifier is 2. Our noise figure for our second amplifier is 3.01 decibels. Well, now I have some important information. Let me go ahead and clean this up. Now here's a little curveball. I need to know the gain to find my total noise ratio. That's where going to be our curveball is. Now this one, I kind of made it easy on you. So if you ever want to find your power gain ratio, it's going to be your gain equals your power out over your power in. And that's going to be your ratio. For example, we'll do our first one. Our gain for our first one is going to be, we have a power out of 10 milliwatts. And that's over our input, which is 5 milliwatts. And that's pretty simple. You plug chug that in that calculator, it's going to give you 2. So you have a gain of 2. You actually multiplied your input times 2 to give you your output. That's how you do gain. You'll see that more in op amps. But that is going to be our gain for our first amplifier. So gain for the first one is 2. Well, we can do the second one now. Gain for the second one. We have an input of 10 milliwatts, an output of 50 milliwatts. So our output is 50 milliwatts over 10 milliwatts. And that's going to give us a gain of 5. So our gain for that one is 5. So always keep in mind what's unitless and what's not. So for this one, now we have our noise ratios, now we have our gains. So we can actually plug and chug this in this equation over here to find our total noise ratio for this whole system. Let me clean this up. So I have our total noise ratio equals our first noise ratio in our first amplifier plus our noise ratio in the second amplifier minus 1 over your gain from the first amplifier. Now I don't need this one because there's not a second amplifier here, so we're going to only use these first two right here. So let me go ahead and plug this in the equation. Our noise ratio total equals our first noise ratio for our first amplifier, which is 1.26 plus, and then our second noise ratio, which is 2 minus 1, and then we have our first gain. First gain is 2. Well, it's pretty simple. I'll bring this down one more time just so that way it's easy to follow. It's going to be 1.26 plus 2 minus 1 is 1, divided by 2 is 0.5, or half in this case, whichever one you want. So our total noise ratio is going to be 1.76. And that right there will be our total noise ratio. Those are pretty simple. Well, I think we have enough information now to go ahead and go find out our equivalent noise temperature. So I'm going to leave these values up right now, and I'm going to go ahead and get rid of this guy. Now we can find our temperature equivalent of each amplifier. So I'm going to say our reference temperature times our noise ratio minus 1, and now give us our equivalent noise temperature. So let's do our first one. Say T, I'll put a 1 there, equals, and this is going to be our reference temperature, which is 290 degrees Kelvin, times, and our first noise ratio is going to be 1.26, 1.26 minus 1. All right, and that's an easy plug and chug, so it's going to be 75.4 degrees Kelvin. So that's going to be our first one. And we're going to do the same thing for the second one, so it's noise equivalent equals 290 degrees Kelvin times, and it's going to be 2 minus 1. That one's pretty easy. 2 minus 1 is 1. 1 times 290, so that one's pretty easy. 290 degrees Kelvin. So we just found our noise equivalent for both these amplifiers. So, and those will be your final answers. Hopefully these weren't really too difficult. There we go. Hopefully there's enough information here to get your feet wet and how to understand how to manipulate these problems. If you have issues going from signal noise ratios to decibels and so on and so forth, we're going to have a signal noise ratio video to kind of help you along on that one. Hopefully there's enough information here for you to get by. If you have any questions, feel free to let me know, and I hope you all have a good day.